Yeah, you can put it there.
I still don't have my organism, so I'm having arts and crafts day tomorrow.
Okay.
Sorry about that.
I mean, I'm about to start, so you do you the. It's because I didn't plug the thing in. Okay, I think it should have stopped. All right, so let's start off with a demo. So we left off, we were actually right here, where they were talking about that fresh water does not conduct electricity. And so I brought a little light bulb today. So my cord is a lot shorter. And my extension cord is short. All right, here's the little probe. So as you can see, this is a nice safe way to do it. So you have this little conductivity probe, and then it's just going to complete the circuit or not. So let's start with, so I have here distilled water. So this is from the lab. Let's see how distilled it is. Trying to see any change?
Will the light bulb light up because of the pH in the water?
Well, so this one shouldn't light up, right? Because there's no ions. If it's distilled water, we're not expecting it to light up because there's no ions floating in solution. So there's no way for those electrons to move. Because that's where we left off, right? So just a quick refresher. Where were we? I think there was a better graph somewhere. Maybe not. Yeah, this is what I was looking for. So, right, we said that if you have ions in solution, they separate and they undergo nucleation by the water molecules, but you have to have these charged ions in the water to get a current. So that's where we are now. We're trying to see that. And so let's test next. This is tap water, at least the lab tap water. We could test other tap water sources. And let's see, so far still nothing. So now let's go in. So now this is 20% sodium chloride solution. So this is pickling salt. Oops. And so now that is nice and bright.
So the salt in the water creates electrons that light up the light.
Well, it creates movement, right? So let's draw a little diagram of what's going on. So we have, and you can see I'm no artist.
That's great.
It looks more like a shroom than a light bulb, but whatever. And so some sort of battery source, power. Yeah, I drew this kind of poorly. Then we have our beaker. That's supposed to be my beaker. Let's try my beaker again. And so these electrodes are going in there, right? So essentially you have a circuit, but we have a broken circuit. So we're asking, does our liquid kind of complete the circuit? And so again, those sodium ions, so they're physically moving around, right? So you dissolve something, but then they don't just stand there, right? All these atoms are moving around constantly. And so you have to think about that, right, on a molecular level. So it's physically the movement. So this little sodium or whatever comes over, picks up an electron or whatever, and then starts floating around and either bumps into other ions, but somehow essentially makes a circuit, or, you know, it could physically flow there as well. But, you know, I mean, this is all the tiny level, right? You're just thinking all these ions, bloop, 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 they're all just like transferring electrons down. So you've essentially just completed the circuit with those ions in solution. And so all we're just emphasizing with this experiment is if you have pure water, right, it would not have the same effect. So just the pure water floating around, that cannot conduct electricity. So this is like kind of beyond the scope, but so covalent compounds do not work, basically. And so we'll demo that. And so what do I mean by a covalent compound? So I brought along sugar. So sugar, if you just kind of look at it with salt, right, they look about the same. They're both white powders, crystals, whatever. But if we try to dissolve some sugar into the tap water, and I should have brought something, not that it'll make much of a difference.
Here, I've got a stir stick.
Yeah, not that it'll help, but we'll at least give it a valiant stir. And dissolve my sugar. You want your stick back here? And so, right, we try to dissolve sugar in there, but it doesn't do anything.
So is the salt,
It's like barely, so there could be a little something in solution or impurities. But yeah, you see it's very weak, right?
so is it the salt specifically that's creating this reaction?
Well, so it's not a reaction, but it's just transferring electrons. So the difference in the structure and what's going on is, again, you need the ions. So you have to have ions in solution to get a real nice light bulb.
So does salt have ions? Is that what you-
Yeah, so salt is an ionic compound. And so the difference is it's held together by just electrostatic forces. So to make sodium chloride, there's a transfer of electrons. And let's just look at some pictures. That'll be, this is what I look at in my other class. So let's look up. So if we look at sodium chloride, and so first let's just appreciate its crystal structure. So again, ionic compound, which is maybe going above the scope of this class, but basically metal plus non-metal came together, so opposite sides of the periodic table. And then the key here is there's no bond between sodium and chloride. So that way when they go in solution, they can get surrounded by the water molecules. So this is a really good depiction of the crystal lattice structure. And so notice the alternating sodium in purple, chlorine in green. But that's a super stable structure, except again, there's no bonds. So because they're ions and they're charged, they go into water. Water's polar, so it can nucleate, meaning surround all the ions, and that's what causes it to dissolve. And then those ions moving around make the electron flow.
Would seawater have the same effect?
Yeah. So I don't remember if you look at, we do the light bulb, but we could bring the light bulb to the lab, because I think we're going to be looking at like pH and salinity. So we could bring this to lab, and you could dip it in the acid too, and see how the light bulb changes with the seawater. That helps. But the difference is just, does a compound make ions in solution? So let's go look at sugar. So let's see. So the problem, so let's first look at, well, if you just look at sugar, right? Sugars are either monosaccharides or disaccharides. And all that means is you might see different formulas for sugars. So they might give you, so this is like the common monosaccharide, so C6H12O6. And so it's a ring structure. Let's look at another sugar. So this is fructose, so like from the fruit. So that one's a 6-membered ring. But what do we kind of notice? What's the difference in these, just in the structure? Look at other ones. So you might see sucrose is a common one. So sometimes if you look up sugar, you'll get this formula for the disaccharide. Well, what do they all have in common? What do you notice about their structure? Especially compared to the sodium chloride.
Because they're more dispersed and more open.
So that's kind of one way to look at it. So like, right, they are dispersed and open, so we're thinking about that. So they don't pack like this does, so that makes a completely different crystalline structure. And there's another thing we can say. So their bonds within themselves are stronger. You're correct, so the covalent bonds. But maybe going back to your idea that they're spread out, is that their intermolecular forces are a lot weaker. So that also contributes to some of the factors. But we're kind of dancing around the dissolving thing. So what?
So like, is it because, so so does the sugar dissolve easier than the salt?
So it dissolves worse.
It dissolves worse, so it's
And then
easier to dissolve salt.
Yeah, but then it also doesn't make something in solution. We're missing like the key word that we need. So what do we need in solution to have some movement?
A vehicle.
Movement in solution. What'd you say? Ions. So that's the key word that we were looking for. And we were kind of dancing around it. But it's the way these structures are. And so you're kind of touching on something. It's like, yeah, they're spread out, but that's because these are now molecular compounds. So these are covalent compounds. So these are covalent, and then you mentioned that they were held together strongly. So that is true. Within the molecule itself, it is very strong. So these bonds are strong. So that's why when you plop sugar in water, right, it doesn't disassociate either. It's bonded with itself. And getting into, now let's look at like acetic acid. And so now taking it a slightly step further, so we have acids. So acids can also have the same effect. That's why I said we might want to keep this out for lab. And so you have two types of acids. This is kind of an aside, but we'll at least mention it. So acids are similar. And so what do I mean by that? And so I started with acetic acid. And so acetic acid is vinegar. And so this is the structure of acetic acid. And so I'm just going to draw this. But basically in solution, so plus water, this proton is called acidic. And all we need to know is that it makes H plus ions in solution. And so if we take this to the lab later on today, and you dip it in your acetic acid, the light bulb should light up, although it will do so weakly. And so why that is, so vinegar, and I started with vinegar, or acetic acid. So this is called a weak acid. And weak acid has nothing to do with how much it hurts when you touch it, it's how much it disassociates. And so all that means is if you have acetic acid versus, let's take a strong acid that fully disassociates, like HCl. All that means is all the HCl, when you put it in water, it becomes H plus and chlorine ions. So then you put the light bulb in there and it's super bright. While as vinegar, it has equilibrium action. It's a weak acid, so there's some still all together as one piece and some as H plus. So then you get a weaker light bulb. And we can play with this in lab and it'll be probably more obvious. But basically, right, you have to have ions in solution, and so we went over, right, covalent compounds then don't work like sugar, but any other ions could. And so you could test like your alkaline water. I don't know if anyone has alkaline water they want to sacrifice, but basically, right, alkaline water though, they put in maybe sodium bicarbonate, a little like magnesium salts, but that's all just creating ions. And sometimes, right, some of those waters, they add different minerals to give it that flavor. That's why people like different water or whatever. It just depends on the minerals that they use. But then you could kind of test it and just kind of get a sense with how bright the light bulb is of how many ions are in that solution. All right, so are we at least clear that we need ions to turn the light bulb on? And sugar didn't work very well. And, you know, that sugar could have been impure too, so we're not quite sure what was in that sugar packet. And so I think we'll do some of this in lab, or at least play with some seawater. And let's see, so we have, pure water, just comparing pure water versus seawater. So pure water, they're both pretty clear. And of course, you know, for seawater, it depends on the currents too, and if the sand's being, what do you call it, like uplifted by turbidity currents or anything. With larger quantities, it kind of turns blue-green, since your water molecules scatter blue and green wavelengths the best. And so the odor, of course, pure water should be mainly odorless, versus I'm sure we've all kind of smelled the ocean smell, where it has that kind of salty or fishy smell. The taste, of course, if you were to taste it, it'd be pretty salty. I'm sure we've all gotten some seawater in our mouth before. And the pH of pure water is 7, and so 7 is neutral on the pH scale. And then pH of the seawater is probably slightly alkaline, so roughly 8. And so because it is full of ions, it has freezing point depression, so aka the freezing point is going to be a little bit lower. So in this case, about -2 degrees Celsius. And then boiling point, you have boiling point elevation effect, so it's a little bit higher at 100.6. So that's why some people say maybe you shouldn't salt your pasta water beforehand, but honestly it probably makes so little of a difference that it doesn't really matter. But people like to have arguments about that. And so density, obviously salt water is going to be a little bit more dense since it has ions in there. So what's brackish? Where do you get that from?
That's in water that's in transition, right, between the.
Yeah.
So, it's like a slightly saltier version of fresh water.
Yeah, so saltier. Fresh water. And anybody know any like creatures that like to be there?
You know, should I had a practice fish tank, so you can have some cichlids like it, or some,
How do you
there's
spell
some
it?
snails that like it.
Sorry, one more.
Yeah,
C.
CICHLIDS.
HLIDS.
I know there's like some,
Aren't there also the mud skippers? We used to have some apparently, but I guess there was like one student worker that could work their magic getting like the perfect brackish water, and then they left and the poor mud skippers died. Yeah.
There used to be a ton of it at, Nui Tai, it used to be downtown. Used to be an exotic pet store, and they had a bunch
Oh.
of brackish, tanks there.
Oh, that's cool. Yeah, I've seen the old logo, I guess.
Yeah, they used to have a Texas armadillo catfish that was like 100 years old.
What?
Yeah, and it was like this big.
What happened to the store?
They got caught selling sick exotic animals, like pythons and stuff, and it was like hurting people.
Awkward. That's unfortunate. Well, so much for that. But yeah, that's really awesome. And of course, you know, like we were saying, to maintain a brackish tank is kind of difficult synthetically, since it's this area, like you mentioned, where your fresh water is coming in to the ocean.
It's really interesting because, it's one of the things that help the salmon and steelhead with their transition from the ocean to
That's
the,
right, too.
fresh water before they get up to like the hatchery and whatnot, so they don't, immediately die from like the shock of their body going from.
Yeah, that's a good point. For the species of fish that are able to transition, yeah, that is an excellent.
It changes their entire everything, like their whole body, their face, their nose, everything changes when they go from the salt to the fresh water.
Yeah.
Well, lots of, things like to feed the estuaries and the brackish water. There's so many small things come down to feed on the things coming downriver, and things like to feed on them, dolphins, seabirds. And manatees love it. They transition through it. They travel up and down the coast in Florida. It's a fresh water, but
That's a good point too, because and vice versa, there's a lot of things that float into the fresh water that, the trout, the other species, the osprey and stuff too. So
Oh, osprey. Of course, we have to put the osprey on there now. Yeah, excellent. So yeah, a lot of. Sorry? Yeah, but they're gonna come
Yeah,
down
they
and
go
hunt,
fishing.
yeah.
They dive like 30 feet into the water sometimes to get their food. I guess wild ape.
Yeah, I mean, yeah, they gotta come down and hunt.
You'll see them, it's super awesome seeing them with like a giant steelhead. Just like,
I haven't seen
struggling
that.
to get up. It's really funny.
That's awesome. So yeah, I mean, this is really perfect because you guys are, making the connections to life and how important all these kind of delicate ecosystems is, how things change, how things travel. And then even thinking back to the lab, some of you were pointing out that you had like all this organic material, so we could think about that, right? Everything coming down, just the plant matter too. So it's really all fascinating, and you can see the connections everywhere.
And that's another thing I just put together too, because I just got done reading like the sediment chapter, was like, there's a distinct transition to like, where it goes from that muddy clay to the more gravel, rocky limestone bottoms in a lot of the rivers we have, so I thought that was interesting too. Just knowing from spending a lot of time at the ocean mouth and the river's mouth,
Oh,
seeing
yeah.
the differences now.
Yeah. Yeah, it's pretty fascinating. And of course, so the kind of, I guess I would call it the opposite from brackish is then hypersaline. So of course, hyper meaning high salinity. And so usually this is some area with some high evaporation conditions, and then of course that just leaves behind excess salt. So you have the Great Salt Lake. So it has, I'm not 100% sure what these units are in. If that's parts per 100 or percentage. Maybe that's supposed to be 280 percentage. I'm not sure. Dead Sea salinity, though, is also extremely high. And so why do they always have the picture of the person floating? What
Because
happened?
the salt is, it makes them so much more buoyant.
Yeah. So the salt is more dense, so that means you are relatively less dense, so yeah, it's a lot easier to float, which sounds fun. Never experienced it. Has anybody been to any sort of salinity pool or where you really float?
Is that like the suspension tanks or like the deprivation tanks?
I've done one of those.
Where you're just sitting there and
It's
Oh.
really scary.
Yeah, I don't think they put salt water in like the deprivation tanks though, but,
Wasn't that how they get you to float?
oh, I'm not sure, do
No,
they?
They add salt.
Oh, okay, I didn't know that.
So you like float on the surface.
It's
Oh,
your
cool.
Body, so they make it your body temperature and they take away all senses, so you're floating there and like your body temperature is water
That-
and then it's dark and so,
Yeah, that seems scary to me, but,
yeah, people have like, it goes in one of two ways, like it's really good or it's like a psychotic mental break.
That anxiety was not.
well, that's pretty cool. I didn't know that they made them super high of salt like that,
Because
so you
that's
could
also how
float.
they do displacement tests, right, for body fat.
I think
Just
so.
water.
Yeah, I'm not sure how
They
they,
put you in there and it showed the, because of how salty or how, whatever the water is. When you get in, it shows your displacement of it, and that's how you get your body fat percentage, like the most accurate body fat percentage.
yeah. Excellent, so many uses. And let's see, so going back to salinity, so decreasing salinity, obviously when you're adding fresh water to ocean. And again, I think y'all can tell me lots of examples, melting icebergs, melting sea ice. Have y'all been out to the Oregon caves recently?
I'm going on the 11th.
Oh, yeah, you should totally go. Maybe we should even do like bonus credit if you just send me a picture of you there. But yeah, so did y'all see like the massive erosion too that has happened from the snow? And like, yeah, one of their buildings there was like shifted, so they had to close it. So. Yeah, totally cool to check out the Oregon caves too for other things because they have the fossils there.
We also do candlelight tours.
That's I haven't done that. That sounds fun though, or scary. Yeah, but I'll totally. Should we do extra credit for that then?
Yeah, we should.
So extra credit if you just send me a picture from the Oregon caves, or if you go anywhere else really cool.
I did, that's in Newport, that we were gonna go. Have you been to like the Devil's Punch Bowl
Mm-mm.
So
in
cool.
Newport?
That's cool.
It's this crazy tide pool that it's super dangerous most of the time.
Yeah.
But there's like a 2-hour, like time frame depending on the tides that it's safe to go down there.
That's cool.
You can literally get inside of it if you
Yeah.
get there early enough. It's super neat.
So yeah, I'll open up extra credit then, probably like 5+ on an exam. Just send me a picture. So I'll say from Oregon caves, but if you go somewhere else really cool, I'll probably accept it too. So I just put more suggestions. Crater Lake's also really geologically fascinating since that, I mean, they say it was just what, like 700 years ago, a volcano collapsed and then made that lake. And then it's also like really strange because it's super blue and the level doesn't fluctuate. So it's like really strange, like natural phenomenon.
Well, it's ice cold and it's like super clear too, so you can see to the bottom, like you can see
Oh,
like
that's
100 feet down.
crazy.
No, it's all rainwater, isn't it?
I think they don't, I've read that they officially don't know. Because like I said, the level stays so steady that like they don't know if there's some underground feeding that keeps it level or, yeah, if it's just rainwater or how. They're really not sure. It's a cool mystery.
I wanna go there this summer. I've seen it, I've been there, but I saw it from the air.
Oh,
This
cool.
month, or no, in June, and I did not realize how huge it is.
Yeah.
It's really big.
Yeah, I actually haven't made it to Crater Lake either
There's
myself.
huge fish in it.
Oh, man.
I highly recommend it.
Yeah. Oh. Isn't it like 33 miles or something?
You have to do it in chunks, absolutely.
Wow, that's awesome.
I've been there, yeah.
So yeah, definitely, if you find some cool features, send me a picture or whatever. And so of course, anything that can increase salinity, you're removing water from the ocean and that leaves behind saltier water. So that could just be from sea ice formation, and sometimes too, when you get ice, it'll kind of leave out some of the water from the crystal structure, just kind of depending. And then obviously evaporation is a big one. And this is just a handy chart, but I don't think it's that revolutionary. And you guys can figure it out, right? If it rains or precipitation, you've seen it in all the different forms. Obviously, it adds fresh water. Runoff, we saw that. Iceberg melting, that's going to be kind of more fresh water. Sea ice melting, you'll have some fresh water, or excuse me, mostly fresh water, some salt, because like I mentioned, some of those ions will be not incorporated into the crystal structure. All right, let's keep, and then this is just what else is in your water. So lots of bicarbonate in there. So that's bicarbonate, and I think we talk about this in lab, but it's just basically the hydrated form of carbonate. And so, right, we really mentioned everything's a lot of equilibrium. So we mentioned acid in the ocean gets neutralized by calcium carbonate. So then that calcium carbonate can be acidified in solution to make bicarbonate. So that's why you have so much of that. Then, right, what do we mention? So all of our creatures are made up of a lot of calcium carbonate. And so it makes sense that we have a lot of calcium in there as well. Silicates, so again we said a lot of our creatures are made up of silicates as well, or quartz. So quartz was another rock, super common rock. We talked about silicates and calcium carbonate, and I'm sure you saw probably little bits of quartz in your sand samples. And so then of course just other ions floating around, so there's a lot of sulfate salts. And obviously there'd be chloride, sodium, magnesium, potassium are also fairly common. And so this is just kind of putting it all together. So what do we think hydrologic means, or hydrologic cycle? Fancy word for water. So water cycle. And so of course, right, we've seen again how the salinity is affected, and obviously this recycles water among our oceans, atmosphere, and continents. I think we have a really good kind of sense of that here in Oregon, even just, you know, thinking back to the snowpack, all that runs down into our rivers, and of course the rivers start flowing, right? That's also why, isn't it the most dangerous to kayak at the beginning of the season, right when everything's melting and you have that, all that new runoff? Yeah, so high flow, so you can even get into a little bit of fluid mechanics there too. So right, all that water, thinking back again, all the material that it's coming down from the snowpack, the trees. And so now we're looking. So this is a good picture. And so for your exam, this would be a nice picture. So I'm doing a lot of like graph labeling for your exam, hopefully. Again, it's a lot of big picture ideas for your exam. At least that's what I'm going for. But this could be like a good example. So just labeling, so we have obviously precipitation. We see that locally. Then all our local rivers, the rogue rivers, and I'm sure you guys know the rivers much better than I do. So I just got here 3 years ago. And of course, all that, right, feeds back into our groundwater, which is super important. And let's just talk a little bit about local issues. What's the issue with the groundwater? Or just the water in general? Who's using the water, though?
Marijuana farmers?
Yeah, so the marijuana farmers, they're causing issues. And so this is, right, a big problem. So, right, our marijuana farmers, especially illegal grows. So they're using up all the water, and then that's taking away resources from our other local people. So, right, people that grow the pears locally, pumpkins, everything.
Not only that, but I was told in our area, a lot of our wells are going dry, and they said that's the reason.
Yeah, so all that's related. If people start overusing and, taking more than their fair share or whatever, then yeah, exactly.
People need it more than marijuana does.
Huh?
I said people need it more than marijuana does.
So it's growing in unpermitted places, and particularly with the wells, because like for irrigation rights, it all comes from the ditches or from direct rights on creeks and rivers, and you're not supposed to pull those volumes of water from the groundwater. So that's how it takes out patches of the things. Instead of irrigation ditches or river access for real water, there are places where they're pulling it from groundwater.
I also saw somewhere that
No.
whatever's in the marijuana, when it's in the ground, it's actually causing issues in local street, like, I think it said it was making the water more acidic. And it's
Oh.
throwing out
Phosphorus
gases.
blooms,
Yeah,
phosphoric acid.
And it's actually
It's-
killing the ecological environments that, like we've had issues with the things that live in it, the vegetation around it, just getting destroyed because of
High
abundance of
phosphorus
marijuana.
levels encourage anaerobic bacteria. Anaerobic bacteria love spitting out sulfuric acid.
Then you got the
It
cattle
raises
stomping
acid level.
the banks and making the water thinner and shallower, which is warming it up and causing, so it's like, there's not a whole lot of things fighting our water system right now. It's just taking a beating.
Yeah.
The phosphorus damage, like in Florida, it's horrible from the oranges. And
Oh, really?
legitimate agriculture. When I grew up, there was an average of 150-foot visibility in Florida Bay. Now, if you get over 25 feet, it's a good day. And that's all thanks to the same practices by legitimate things. Just because it's moved in and they feed cheap phosphates, especially the cartels and a lot of the illegal grows, because it's going to be your cheapest thing. It's just a straight chemical salt, and they just throw it in, and they're the ones usually pulling groundwater and importing that, post irrigation rights, because they're charging more for the lease, and all of those things. But any farming that shows no regard for the environment or community, it's kind of crappy. Because you destroy groundwater in Florida growing up.
Yeah, exactly. Yeah. I mean, I think it's awesome. So, like, to take away with that, it's like, this is great to look at and study in class, and we look at this, but then we have to understand, like, why is it so important to protect, our resources just in our backyard? And, like, I would say to y'all, like, get involved in your local politics, pay attention to things. Like, people also always get sidetracked by, like, the national conversation and the presidents, but at the end of the day, it's kind of like, who really cares? Let's look at what's going on in our backyard, our neighbors, what works for us, because, we have to protect our valley for the future. And, we're seeing the importance of it. We're kind of getting into the chemistry. You're telling me about the phosphates. It's all related, right? So it's all big picture, small picture. But ultimately, you have to get involved. All right, back to big picture. I know we're zooming in and out everywhere, but y'all are awesome. And I love hearing more about our local issues, because that's what we need to always, focus back on. All right, so then we mentioned the runoff, so we see that here. And of course, if we go out to the coast, then we see it run into the ocean. And so obviously, all along the path, there's going to be some evaporation. And we mentioned, of course, a lot of evaporation comes from the ocean, thinking back to those hotter kind of evaporation belts. And so this doesn't happen on our kind of west coast. But you probably know, being on the Gulf Coast or somewhere where there's warm water, you can really see that cycle of evaporation and precipitation really quickly. So like in Houston, especially during the summer, all the hot water from the Gulf goes into the clouds. And then by your 5 o'clock commute time, it's pouring down rain. And it does that like every day during the summer. I'm sure Florida probably does something similar.
From 6 to 5 o'clock.
Yeah. So same thing, you see that happen really, really fast. And right, anything else we want to say about evaporation? So again, this could be a chart on an exam. So again, we see precipitation, evaporation. And yeah, just excellent, everything that you were saying about irrigation and also volume control. So at least we're understanding, why they say, how much to pull on a well, all that's related to our groundwater preservation and just making sure everyone has resources. Those are all good points. And so again, why this is important, most of our water is in the ocean. Then we have the problem of how do we desalinate it, and we could go down the rabbit hole of desalination, but we won't today. So I want to say Egypt practices desalination, a lot of the Middle East, but for us, probably not cost effective. And then more fresh water, or more waters in the glaciers and ice caps, and then groundwater streams, water vapor, and so this is our fresh water, so just a very small percentage. I know, but that's just like how big the ocean is, right? And how deep. Like, I know, it's crazy. So you have to, I know, try to wrap your head around it. It's amazing. But that's just really a testament to how big the ocean is.
Well, it's really funny because I never really thought about it until this class. And they show you see a map on the wall most of the time. I hardly ever see a globe anymore. So you kind of forget that when you're looking at where all the land is, that's it. And on the other side of the globe, it's just ocean. So it's really that like a realization this class for me again was like, oh, that it was really that big.
Yeah.
Random trivia, which country on earth has the most fresh water? Everybody. Canada.
Ah.
Yeah, they're saying it's like freshwater prices have been increasing at almost 2 to 3 times the rate of gasoline over the last
man.
little bit. So I remember as a kid in the 70s, and everyone was like, selling water, that's the funniest thing ever. You have to say by like 2050 or something, Canada technically resource-wise is going to be one of the richest countries because their water fields are almost going to be above the oil fields and more.
Huh. That's cool. I know, we won't go down. That's like another rabbit hole entirely of like bottled water, and like some are worse than others.
It's like wells are a blessing. Like we're out by Williams, and we're on a well.
Oh, that's
Almost anywhere around the Pacific Northwest, you can have a well.
yeah. Yeah, there are a lot of wells here. And so this is just definition. So we have this thing called residence time, and that's just average life cycle of a substance, how long it remains dissolved in seawater. So ions with a long residence time are in high concentration, and ions with a short residence time are in low concentration. And of course, we can have our steady state conditions, so just the average amount of various elements remain constant. And again, right, you'll see that with bicarbonate, sodium. And so what this could also be referring to is, I remember we were talking about volcanoes, right? So you could try to track that life cycle. Where is the origin of these different sulfates, chlorides, I mean.
I'm so sorry, can you just, I lost the website, but thank you.
And so again, that just goes back to trying to track either ocean currents, air currents, just seeing the effect of everything. You could probably even try to measure, right, the fires, although now it looks clearer. I don't know what happened. I haven't been following them. But just tracking those types of sediments. And again, right, carbonate, calcium, sulfate, sodium, kind of seeing those again. And so they are added to the ocean from just discharge, volcanic eruptions, of course, hydrothermal activity. We could probably also mention large vats of limestone help contribute just in the ocean. And then, of course, ions are removed by either some sort of precipitation. Again, thinking back to those little sea creatures and how you had a buildup of either the silicates or your calcium carbonate deposits, like with the coral reef. And of course, ions can go back in to the crust as well, of course, looking at like the seafloor spreading, so at a mid-ocean ridge. So of course, a lot of hydrothermal activity. We'll just highlight that since it's a good in and out point for ions. And again, just thinking back to our organisms that then leave behind their shells. So now we'll do a quick pH overview. So we mentioned, and so this is the most basic definition of an acid and a base, but this is not all-encompassing. But we'll just stop there before I get overexcited. So we'll just take the simplest definition of an acid. So it releases a hydrogen ion when dissolved. And so all that means is, like we saw with HCl, so it disassociates. Or acetic acid. And again, in the equilibrium process, so it disassociates.
I'm a little confused because I don't understand, I think disassociates. Just, that sounds opposite of what I put in my head when we were talking about it last time. So I know I can't have it right if it's opposite.
Yeah, so disassociation, because first we were talking about that in the context of sodium chloride.
So I don't know chemistry like you do, so all your drawings aren't really relevant to me.
So, right, you have, all we're saying is you have sodium chloride, right? It's an ion in solution, but, you know, I don't want to overcomplicate it. So we're just thinking about sodium and chloride. Then they go in solution, but, right, we mentioned that they can get nucleated. And so all that means is they separate into ions. And so, right, go back to the picture. This is what's happening on a molecular level. So I just don't want to.
The little red points.
Yeah, so the little.
Separating, and I'm like, that's all.
Well, because we have to, it's showing you how it's separating. Sorry, I threw down my pen somewhere. I got too excited. Oh no.
So those two are the same, but they switched and separated?
So, yeah, so in the water,
So you're
here's
talking
my
about
pen.
the positive charges that pulled away from the nucleus?
Right, so this is showing water, right? So the little red ball is oxygen, the white balls are hydrogen. So all this is saying, and we mentioned that water was polar, so there are a lot of reasons why. Part of that being is it has these lone pairs, but let's just redraw it oversimplified like they have. And so basically this half kind of has a partial negative charge. Let me redraw that, partial negative. So this side feels more negative, like a magnet. So just think of a magnet, right? North, south, or whatever. This is oriented positive. So then when you have those ionic compounds, anything that can make ions, anytime they hit water, they split. And so they do this sort of thing. And so all that means is on the molecular level, right, this oxygen is like, hello, sodium, you're so positively charged, I'm going to hang around you, right? So that's all it's doing there is orienting its negative charge. And then it's going to nucleate, So all the term nucleation means is it's going to be completely surrounded by all your water, basically. And so they just drew this as more of like a 2D planar view, but there'd probably be like a water on top, right, a water on bottom. So it'd be completely surrounded. So that's like on the microscopic level, the atomic level, what it means to start with like a big piece of solid sodium chloride crystal, dump it in water, and then it just disappears, right? So why does that happen? So this is why, because of this nucleation.
Well, is this purple and green the little particles that separate from salt?
Yeah, so this is just sodium and chloride, so I keep getting excited and throwing my pen everywhere.
Okay.
So yeah, all they've drawn is this process, right? I write it just shorthand like that because we don't want to draw, every time the water molecule is coming around. But that's what's going on. It's just in water, and we shorthand it as just it's disassociating, like that.
So, is nucleated basically sort of like the center of a jawbreaker? When you break it, there's that little thing, and then it's surrounded.
Yeah.
And disassociated is kind of just like not hanging out anymore. Like the sodium, you've got the, like sodium chloride. When they disassociate, they just become sodium and chloride instead of being sodium chloride.
Exactly, right? So disassociate is just break apart.
Yeah, not
They
hanging
break
out
apart,
anymore.
yeah. And again, they can do that because there was no physical bond holding them in place anyways. So it's just that electrostatic potential is what we say help hold them in place. But then they disassociate once water can like just physically, literally come in between them, right? Because it is attracted to either the positive or the negative ends. So then back to here. So acids do the exact same thing. So that's why they can light up the light bulb in the exact same way. So I could run in and grab some acid if we're really chomping, or we can wait till lab. And so it's literally saying the same thing, and it's like an instantaneous thing. So you put, right, HCl in solution, but as soon as it hits it, it's going to disassociate. And this is kind of the oversimplified process. Because what's really happening is you would never have H plus naked by itself in solution. What is truly happening is your water comes along and instantly plucks off this hydrogen as soon as it sees it and makes formally hydronium. But it's just honestly chemists are lazy that they don't draw hydronium a million times, so you see that as H plus. So if you ever see this in textbooks, so hydronium is the same thing as H plus for the most part. They're used interchangeably. All right. And then so back to the vinegar and kind of the difference. And this might be too much chemistry, but basically it just plucks off this hydrogen and you make this ion. So again, they still disassociate, so the main thing you want to take away is it's losing the hydrogen. And this is kind of beyond your scope, but when I say a weak acid, right, going back to the equilibrium, all it's saying is like part of the acetic acid is disassociated and part of it is still together. And then they can go back and forth. So after they're disassociated, this could come back, pluck back off this hydrogen and reform your acetic acid. So does that make sense? And so again, we'll kind of put as an aside that weak acids have an equilibrium, but that's kind of beyond our scope. So strong acids fully disassociate. Weak acids have an equilibrium where some of it is dissolved or disassociated, some of it is not. So I'll put some disassociated.
So like, it might be different at the top layers of like, say, seawater versus like lower level seawater.
Yeah, so
It combined back together, but then it can also dissolve more.
yeah, so what you're thinking of more, and we might get into that, is the CO2, because that's what you're getting at is, right, so CO2 is more dissolved at the lower levels, so then it's going to be more acidic because more of it is then can make your carbonic acid, so that gives you somewhat of a gradient with that carbonic acid.
Okay.
Yeah, exactly, and yeah, the carbonic acid is even more convoluted because it has like 3 equilibriums, so everything, and we could even just write it out, not to, you know, stress anybody out, it's just kind of appreciate the process. So if I just start with carbonate, you add it with water, and you make this HCO3 minus. Then that can go again, but notice it's in equilibrium, so they can go back and forth. And this can react with another equivalent of water. And so this takes you to carbonic acid. And so now you can just go back and forth. And so technically carbonic acid can eventually come out as CO2 and water again. And this is how you make carbonic acid. You dissolve it together, and then they combine. But right, you can see this is a big equilibrium problem. So you dissolve some CO2, make some acid, but then it might disassociate. So it's all back and forth. And then your carbonate, right, is your base, again, from your calcium carbonate source. So that can neutralize, right, acidity in the ocean. Again, go back and forth. So it's all one big complicated equilibrium.
Is like these chemical formulas that you have a text, I don't.
No, see, that's why I said I put them on there. I put them on there so we could look at it and appreciate why this is a complicated system in the ocean. But yeah, I'm not trying to stress anybody out with all these chemical symbols.
So I had a quick question, being that we have a test on Thursday, I'm seeing that our textbook offers kind of like a practice quiz and visual representation aid through masteringoceanography.com. And it says that as long as we have the class code, like the instructor's course ID and an access code, we can have access to all these study aid materials that would be able to help us potentially understand the course better.
Have you tried plugging in the resources that are online? I think there's like, I haven't tested it myself to see if it works.
Yeah, and I downloaded the PDFs just to see what it looks like, and it looks very interactive, like especially for people that are more visual learners who don't learn as well from just reading jargon on a textbook.
Right, but so did the code not work then, is my question?
If you look in the course information folder, there's a little section that says access in mastering oceanography, and it has the course ID right there.
Yeah, and if it doesn't work, I think I can generate like a new ID, but I don't know how all that stuff works. I don't know if they're gonna try to make you buy stuff. But yeah, I don't think it's necessary. Again, I'm trying to keep the exam big ideas, you know, looking at pictures. All right, so let's continue. And so basically our pH measures our hydrogen ion concentration. So if we have a pH value less than 7, it's going to be acidic. A pH greater than 7 is going to be basic. And then at 7, it's considered neutral, so that's pure water. Yeah.
And is pH
Uh, yeah, because it's actually logarithmic, but I don't think I was going to make you do calculations, at least not for this exam. And so seawater is slightly alkaline. So like we mentioned, the surface is 1.8, and the ocean water pH decreases with depth. So again, you were alluding to that. And you also have differences. So again, everything's in equilibrium. So low pH is caused by marine animal respiration. Have you ever done the boiled cabbage thing to detect CO2? It's something kind of fun. I'll just put it out there in case you ever get bored.
I thought it was cabbage with my girls for a science project, and I think, if I remember right, we added vinegar at one point to change the color.
Yeah, so same sort of thing. So if you ever get bored or want to play with like your kids or whatever, other kids, so if you have some red cabbage, you can boil it, and it's just a natural pH indicator. And all that means is that it changes colors when you change the pH. It makes different colors. But what's cool is you can see how your breath can change the pH. So once you make this red cabbage indicator, it tells you to blow in there, and so you can watch the color change. And so that's just based off of your CO2. And so going back to why CO2 is considered acidic, because it makes carbonic acid. So all one big equilibrium. And so this is supposed to be the pretty colors that it makes. And so red cabbage covers the whole range. And so you mentioned if you were putting in vinegar, it probably went to a nice pink color, right? And as you blow in, it should go more basic. So I'm not sure how basic it will go. I've never actually done it myself with the blowing.
There were two, maybe three things we did to it that changed it. It was really cool.
Yeah, and you could even just like, if you're really bored, test your household substances with it, depending how bored you get. So anyways, right, lower pH, so we can see that effect in the ocean, since you have all those animals breathing out carbon dioxide around this level, and so that's going to make it slightly more acidic there. And again, we're looking at small fluctuations overall, and part of that small fluctuation, again, goes back to this whole system. Everything's one big acid-base neutralization system. And so we had our spike there, and then follow this general trend. And so then, again, I keep emphasizing everything's a buffer. Excuse me. Everything's a solution. And so this buffering, again, keeps our ocean from becoming too acidic or too basic. So we can either have precipitation or dissolving of calcium carbonate. So again, it depends on kind of your pH. So if it's more acidic, right, it's going to dissolve more calcium carbonate to neutralize that acid. But then maybe it gets too basic. You start having a lot of carbonate in solution, then it might drop out. Like, again, we see with the coral reefs or anywhere where you have that high concentration. And so again, oceans can absorb CO2 from the atmosphere without a lot of change in pH. So when we talk about CO2 and all that stuff, I mean, honestly, I think there's after your money, but I won't go down that rabbit hole either. But, right, everything's in equilibrium, everything's a big sink, so your ocean can really dissolve a lot of CO2 as well if, I mean, the levels get high, but anyways, I don't want to go down the CO2 rabbit hole. And so this is just more pretty pictures. So these pictures are what I was drying out as well. So again, just looking at our CO2 can get dissolved, plus water makes the carbonic acid, and then it kind of depends. So it can disassociate, so it shows the first disassociation here. So it actually gives the same information as I wrote here, just in a different form. And I could rewrite the chemistry. But they're just showing, right, the same thing. So step 1, dissolving, making carbonic acid. I'll do equilibrium. Actually, everything's in equilibrium. So they've shown there as a first step. Then it says, and I mean, again, they're kind of doing an oversimplification because it's always going to be partially disassociated. But if you want to get into the math on this, you can take my Chem 200 level class and we go into the math. Lots of fun. No calculus though, just a lot of algebra. And so that's all it's showing. Here, our first disassociation, I'm just redrawing the chemistry. And then it shows there a second disassociation. And then it mentions something if it's too acidic, right, it can go backwards. But that's all I'm showing here as well. And there's our carbonate ions, so if they get too concentrated, it can pile up there, or of course redissolve, you know, again, everything in equilibrium, just depending what it needs. And so high latitudes, this mainly makes sense, right? Well, how else would, there's no way seawater can jump up there and the evaporation just takes the water. So that's going to be lower salinity. And again, we see that very locally with our precipitation runoff. And maybe if you take a, what's it called, a cruise, you might see some sea ice melting. And so low latitudes near the equator, then as long as you have high precipitation and runoff, that's going to lead to lower salinity. Again, just kind of makes sense. And mid-latitudes, you have higher salinity, and warm, dry air increases evaporation. And so this is just little fluctuations around our, depending on your degrees latitude. So again, relatively small deviations in salinity, but at least you can appreciate how it changes near the equator or the tropic, kind of depending on how much evaporation or precipitation. And so again, just another table. So ocean salinity is lower, closer to land, which makes sense where you're going to have your freshwater runoff and all that. Blah, blah, blah. And so density increases with decreasing temperature, and density also increases with salinity and increasing pressure. And so these are just definitions. So pycnocline is just where you have an abrupt change of density with depth. Let's see, we can look at, where's our density? So density, so looking at the depth here. So notice just a drop off. And again, still relatively small scale. I just want you to appreciate the small scale that we're looking at. But there's still a relative drop-off once you get down to 1,000 meters there. So that's all that that refers to. And so thermocline is just when you have an abrupt change of temperature, so therm, that gives you temperature. And so again, you see this around 1,000 meters again. And so in our higher latitudes, you don't have as much of a change. And so that makes sense, right? Around the lower latitudes, you're going to have a lot more sun influencing that, influencing like your surface versus your higher latitudes, where it's going to be more homogeneous throughout. And so there's kind of three distinct layers then. So you have your mixed surface layer that's just above your thermocline. Then upper water is where you have your thermocline and pycnocline. And then, of course, your deep water is just below that. And again, in the high latitudes, it's a lot more consistent, so not as much variation. So then your book mentions desalination. And what is a property of water that makes desalination difficult? We mentioned it, I think, last week. What's difficult about water? It's what? Formed? It's a property related to polarity. I'm looking for a word. Ion?
I don't know, that was the answer earlier.
Try again. Yeah, so you're at least on the right track. So that was specific heat, right? So it has a high specific heat. So we were saying, right, water takes a lot of energy to either heat up or cool down. But if we think about that, so desalination usually requires some sort of evaporation is the basic principle behind these desalination. But so the biggest energy suck is just literally heating up the water. So you have to heat up the water to boil it, right, to traditionally remove the salt, and that's obviously pretty expensive. And so, you know, there's other reverse osmosis or whatever techniques, but I think those are also pretty expensive. But generally, people just think of like the energy required to heat it is a lot. So that's the basic barrier, is that property. So like you were saying, that all goes back to polarity and the hydrogen bonding. Remember, those hydrogen bonds are what give it that property especially. So hydrogen bonding, so it bonds really strongly, has really strong intermolecular forces, but now that makes it hard to remove the salt from.
Marijuana.
Yeah.
It's still in the environment.
Yeah, and I mean, you could argue that maybe, you know, it's not. So you're right, right? Like everything's a cycle, so it's being replenished. But then if it's being misused by people, so that's where the whole
Rates of use
The
versus
rate of
the cycle.
recycle is probably
yeah.
now, so if you're using two but you're only getting one back, you're at a loss.
And I mean that, yeah, because it gets into like big global patterns too of like how much rain do we get, and that shifts over time as well, and just varies year to year how much like yearly rain.
Yeah,
And
groundwater, you need precipitation.
yeah, and then the groundwater has to actually like seep in and make its way all the way to the aquifers.
Certain cities are pulling too much from certain rivers, and so then even the river keeps being maintained.
Yeah, exactly. So it's usually you're right in that, you know, we have a lot of water, it gets recycled, but it's usually being mismanaged somewhere, and it, you know, this opens up all sorts of like rabbit holes, and I'm sure there's a lot of controversy too with each local area, like dams, for example, can be controversial. Sometimes, you know, that doesn't let the water flow anymore, and that might restrict it downstream, but then, you know, there are other reasons for having the dam, maybe to protect something. Like, it gets really complicated really fast is what I'm saying. And that's why I say get involved in your local politics and understand your local area better. Because, sorry,
Illegal to collect rainwater.
wait, it's illegal to collect rainwater in Oregon?
There was a guy that sat in Jackson County jail for 5 years because he was collecting rainwater.
I,
Yeah, this was like 10 years ago.
see, I feel like that's a law that we should change, like, yeah, I feel like I had heard that before, but I
Because a
wasn't.
lot of farmers started to do it, and environmentalists were worried that it was gonna make it so you couldn't have your flows into streams and everything because of rainwater.
Well, that seems silly.
You can collect it now, but it's on a smaller scale. Like you can collect the runoff from the rooftop and stuff. That's illegal.
Yeah, but that's how we established that they were.
No, I know, I'm just saying scale.
Yeah.
You can collect rainwater, but just not on that large scale.
Oh, okay.
If you're interested in collecting small scale, OSU has a thing, it's like a how to collect rainwater from the rooftop. It shows you like how to build a little reservoir and everything.
I just Googled it and it says only roof surfaces may be used for harvesting rainwater.
Okay.
Yeah, the guy who got caught, he had this big ordeal, like a water plant almost, where he was collecting, I mean, it was wild. I still don't think he should have done it.
Yeah, I mean,
I
that
think it
seems
was a
crazy, but.
resource, but
He's trying to make it on his own.
Yeah. But I mean, this is great discussion because you're seeing the issues, right? So how do we more efficiently recollect our rainwater? And a big issue that I've noticed too when you start studying the water and the whole water issue is so when we start paving all these cities and put concrete everywhere, then there's like nowhere for the water to go back into the groundwater. So to me, that's kind of like a bigger issue. And that can cause a lot of issues when you concrete over and make a huge city. Then you create a water crisis essentially because now you can't refill your own reservoirs. So then that can put a strain. And so it's all some, it's a lot of stuff, obviously. This is all very complicated. But that's why we want to look at it at our local levels. How can we use our resources more efficiently? How can we recycle our water? How can we make sure our groundwater is being replenished? All these questions, and it's.
When rainwater is going into those like storm drains and stuff, doesn't that get recycled and stuff?
So it depends where the storm drains go, whether they hook up back to like municipal city water, or some of them lead out more towards like streams or the ocean. So it kind of.
And also the hard surfaces, it just sort of collects contaminants, like motor oils, the easiest one. So then when water does hit it, it's not only going into the environment, but it's hitting it in high concentrations. So like I lived in Washington for ages, Florida, basically the water sensitive areas, and then a lot of it can get these high concentrations, and so a lot of it will run off directly to the sounds, streams, to those things, and then the life there is getting injections of concentrated contaminants all at once, and it builds the level of sediments, all those things. So it's that impervious, the concentration collection is outside of just how harmful the things are themselves. It's when it's dry and it collects and then it rains and it all sort of rinses off. It's like the difference between, salt making the soup taste good or trying to drink seawater. Like it's a tremendous concentration.
I imagine with it
A
being
negative effect.
concrete and whatnot, on a hot day, I'm sure a lot of it's evaporated before it even gets to some of these.
Oil doesn't
these
evaporate.
drains, these.
Pesticides don't evaporate, they just build salt.
Yeah.
No, I mean, no, I'm talking about.
You're talking about the water.
Oh,
Yeah, I mean, it
I
depends.
mean,
I think a lot of it though would run through, but yeah, he does have a point, like especially when you have that initial rain, like if you haven't had rain in a while and then it rains, then that's when you really get all the motor oil, all the anything, right? Runoff from the farms getting concentrated. So it's all.
You guys didn't even mention microplastics.
Oh gosh, we don't want to open. That's my favorite. That's either my worst nightmare and what keeps me up at night, or my favorite topic to go down the rabbit hole of. So yeah, and then there's like, how do you even get microplastics out of the water? That's another issue. Like, how do we treat our water? Like, if we could just do a bunch of field trips in here, that would also be fun. Because I would say like we should take a trip to the Medford like water treatments plant is pretty cool. I know my husband's been on a tour and like seen it, but I want to take a class there because it's just so fascinating and just the amount of work, you know, always testing the water.
There's a water treatment plant here in Medford.
Yeah,
Is it not on the LA outskirts near Lake City?
I thought it was closer, like McAndrews and Columbus.
Oh, there is one.
There
Okay.
is, yeah, I just passed it.
But yeah, even if you could like contact your local water treatment, maybe you could get a tour. Like it's good to know like just what happens at the local level. Like that's what I'm talking about. Get involved, just learn. Like what do they do? Like it's all important of being a good citizen. All right, so distillation, blah blah blah. I think we kind of mentioned this. And if you were ever stranded on the ocean, you'd probably want to make yourself some sort of makeshift desalination plant, right? So the general concept and what they're doing here is you could have just some like inner bowl of water and then have an outer bowl and cover it with something, and then the sun would work so you could collect your fresh water there. Reverse osmosis is like a little bit different because it passes through these different like holes, yeah, like membranes essentially, and so it only allows like ions of certain sizes through. Yeah, yeah, and so reverse osmosis gets it like super pure, and if you keep like repeating that process, that's where I mentioned like you get to the really pure millipore water. But yeah, this is just the most common technique. I don't know what we wanted to say about electrolysis. Hang on, let me look at the book. Because I know what I would say about electrolysis, but it probably isn't what the book wanted to say. Oh, it's just another way to do it. So electrolysis, so this just attracts the ions to the electrodes. I didn't know where we were going with this. I would have taken it to water splitting, but that's like another, like aside. So you could split water technically to make H2O and O2, and some people want to turn this into like fuel maybe for a car. But I'm not sure where they are experimentally. You guys somewhat familiar with that, where people try to run or want to run a car off of like water, or at least in theory.
Was successful with it and it disappeared.
What?
That 70s show talks about that all the time. About cars running off the water.
Yeah, I don't know.
Stuff like steam powered stuff, so I don't know why we couldn't do it anyways.
Well, steam would be different.
Steam would need like an alternative fuel to heat up water.
Yeah, it's just, yeah, so with steam, it's just like, how are you gonna get some turbine to turn, so that's a basic concept.
Now electric cars, some people just alter that. Use both.
Yeah.
I don't know.
Yeah, I personally don't know enough of like the engineering behind it, but like a nuclear power plant works the same way. It just makes steam. You just use the nuclear energy to heat up water to turn the turbines. So it's just, yeah. But some people have the idea if you could like split this into H2 and O2, and then of course you could use that O2 for a combustion reaction.
Do you think that potentially if we were to go that method, that would turn water into a finite resource? Being that it would be an extra way for it to get depleted?
Probably not finite since, right, there's still like the ocean, but you would probably cause a strain on like, right, the desalination methods, because maybe you'd want to have more fresh water, and, you know, I don't even know how that would work with a car, because eventually you might have minerals building up there, like, I don't know enough about
I
that.
just don't know how that would even, you know, I was a mechanic for a long time, I just, you know, combustion is based on compression. And so when gasoline and diesel get compressed, that's what causes it to combust. I mean, water's not really combustible.
Well, that's why they
What
want
they're
to
trying to
split
do-
it into
Hydrogen's
hydrogen.
combustible.
Yeah. So they're trying to split it into hydrogen and oxygen, and then you burn that again.
The water's the deposit, that would be what comes out of your exhaust.
Yeah. So basically, if you could put water in, split it, and then it would re-burn and make water, is what he's saying. But personally, I don't know enough of like the engineering to know where this is. How successful were they?
They weren't able to get a car started with water, but they weren't able to do it with just pure hydrogen. But what their idea was sticking electrodes in it to separate it to get hydrogen.
Yeah, so it becomes, and you can, now we're getting like down the rabbit hole of energy and like how
They
how
have
this works.
hydrogen-powered cars you can buy, but it's like $16 a gallon for the fuel.
Yeah, that's what I was gonna say after that. So hydrogen,
We'll go a long ways on that.
yeah, Toyota has been heavily invested in the hydrogen car. But does anybody know what the big drawback to hydrogen? Yeah, so it's very explosive. And so let's just put explosive. And so that means that it's really hard to transport. And so, right, if you were to try to put it in its liquid form, that'd have to be extremely, extremely cold. So that's not really feasible. So it's going to be a gas. And then, like, that doesn't work with, like, the pipelines. So, you know, like, right, there's oil pipelines everywhere. And this is why I always reach the conclusion oil is beautiful because you can put it through pipelines, you can easily transport it. So that's a big hurdle with hydrogen is just, yeah, is how do you do it? But then kind of going back, so what he was getting at, and kind of the trick though, is how do you have an electrical source, and this like doesn't, this is where like, you know, the math, engineering, and energy all come into play, but how do you inject enough energy to split water, then make hydrogen and oxygen, combust it effectively, right? Get back out water then.
I think that was Ghostbusters' biggest problem is that even though it produced hydrogen, it was nowhere near enough to run it.
Yeah, and that's a problem. It's like, and you could do this on a small scale. So you could take a battery, put some electrodes in some water, and you would see little bubbles forming. And so that would be your hydrogen and oxygen forming. But then like he was saying, right, how do you get enough of it to actually kick off a combustion reaction? So that's, yeah, I mean,
Well, because with the engine, you're mixing air and fuel, and so to make, I'm not able to picture how hydrogen, and then you're removing, so you're taking water, so you're removing the oxygen for the hydrogen to be the propellant, I imagine is what you're compressing to go boom.
that's what I assume, but since I'm not intimately familiar with it, like I don't know if they compress it or how that works.
I
Like,
think it would just work like a hydrogen car, but your gas tank would just be full of water and there'd be electrodes in it.
yeah.
That's what the ideal is.
Yeah, I just don't know like the energy of it, because how do you put energy in and then get energy out, and then where does that?
I think that's what
And that's the problem with the energy to split the hydrogen, and then when the hydrogen burns, it's losing energy as heat as well. So you
Exactly.
have a
Yeah.
Double-ended heat
that's what I
loss.
was like saying, like an electric car with a battery. I don't know if you have to use both.
Yeah. So basically a lot of engineering questions. So I think we'll move on from that. But
Just like when the kids are kind of cold, you be well known.
but I mean, y'all have a lot of great ideas and kind of again see the issues. And so we touched on reverse osmosis. So again, you're just forcing water through a membrane and eventually makes it pure. There's a technique of freeze separation, where something is frozen and thawed multiple times, but honestly, I never hear about this at a larger scale. And yeah, it seems pretty energy intensive too, and it's also time.
How would that separate
Oh,
anything?
okay, so
That's what I mean.
when you freeze something, so thinking back to water, it makes, right, the crystal structure with all the hydrogen bonding. Let me just get a picture. And so when you do that and it crystallizes out, it forces other ions and gases out. So this is, freeze separation is very effective for gases, I would say. But I would not use it for like ions. Oh, come on. I was trying to find a nice picture. Maybe we got a picture somewhere in our notes. Yeah. So going back to this structure, right, if it's going to the solid state, it's making this nice crystal pattern, and that's going to be forcing out any other ions or anything that doesn't match it nicely. But yeah, this would be used better for gases. So if you're trying to like degas a solvent, so like I've done this on a small scale for research. Let's say you have some solvent that was in the air, but you want to take it into a glove box. You have to freeze it and thaw it at least 3 times, and all you're doing is trying to get out any residual O2 that's dissolved. Yeah, like I said, so you're kind of right, is it wouldn't be very effective, but all you're kind of thinking of is on the atomic level, right? It's making this structure, and so then it would kind of exclude sodium from that. It's all that's saying, because, right, it doesn't fit in as nicely to the structure, right? And it's because when you're making a crystal, you're making a very ordered structure, so it's going to try to get out the ions, but you're kind of right in that it's not the most effective, and you can just see that on the big scale with like rocks, right? So if everything is quartz, but then a lot of what gives the color are the minor impurities. So you can see, right, even though you get a nice quartz crystal, there's still going to be other atoms in there. So you have exactly the right idea that this is not a great technique. And so this is just some idea of it. Yeah, and then obviously the energy that's taken into that. And so just your processing plant. So again, this is why you should take a trip to your local water plant and just see how they purify water. There's different techniques there. All right, I think we're done with that. I need to post notes for you guys. I'm behind. Let's see, I wanted to do just a quick overview, roughly. Except now I'm just all over the place. So I would be ready to know where your oceans are. So again, just like big picture ideas. I'm mainly doing it multiple choice, so I'm still technically writing your exam. But again, just like big picture ideas. I'm going to do one of these longitude, latitude problems. Are we comfortable with those? Yeah, let's do.
Is the study guide that's on Blackboard gonna be pretty accurate to what the test said?
Yeah, it's fairly accurate. The only thing that I've added in there is, like I said, a few conversion questions, and then the latitude
Well,
one.
study guide isn't big picture stuff, there's a lot of very specific.
Yeah, I'm probably taking a more broader approach, but I don't want to say like don't study details, but I'm trying to make it more broad is what I'm saying, with some more math or like more like labeling, because I like labeling diagrams, identifying features. I think that's kind of important. Again, like big picture ideas. So let's see. You might want to know, so big picture with this would be like Magellan. So what's significant about Magellan?
He was the first to circum.
Yeah.
Africa, right?
Yeah, the whole, well, so yeah, he didn't make it, but his expedition did. So he sailed around the whole world,
He was
circumnavigate.
a big part of mapping the oceans around the continent, right?
Yeah. And then, let's see. blah, blah, blah. Trying to pull up my exam. Sorry, I gotta log into my exam. Yeah, I won't have too much like detail. Pulling up my exam. Yeah, just kind of big picture ideas of like what was difficult during navigation. So they had issues with the longitude. And just kind of, you know, big picture understanding that. There's a question about the Polynesians. And so just kind of what clues did they use to tell that there was an island nearby? Do a quick review.
Is that the birds?
So birds, what else?
Wave shape as they curve around islands.
Yeah, so birds, wave shape.
I think the shallowness of the ocean.
Yeah, so ocean depth. So good. So again, just kind of big picture ideas. So let's do, someone said let's do a quick review. So given that Greenwich is 6 p.m. and you are noon, what is your latitude or longitude? Sorry. We'll give everyone a few minutes for that. Yeah.
Put it on, you do, what is it, east 90?
East. Yeah, so I think it should be west, right? So
Yeah, there's one
Greenwich.
on the left.
Yeah, you're
You're above. if
You're
If
behind.
you're at noon, you're before Greenwich, so you're over by Africa, you're not by California. Isn't that the east?
no, but if they're at 6, they already are past noon, so you're behind because it's 6 p.m. And then if you're at noon,
Central Standard Time. I got
Yeah.
east west wrong.
so then you'd be west, and then so what's is so west. Excellent. So west 90.
And can you do another one of the other match, the conversions?
Just like practicing a conversion.
Yeah, just so I can make a note of them so I can practice them somewhere else.
So given there are 12 blips in one floop, convert, oh no, convert 20 floops to blips. Yeah, so you could, on the exam, I'll give you a conversion factor. So my point with this exercise is it could be anything and anything. So I'll give people, I heard one answer. And I'm just writing it the long way. So I've heard whispers of 2 of the same answer. Is everybody there? Give people another minute before we really shout it out again. what do we get? So 240 blips. So I would expect that. And then, so let's go back to your study guide. And so all this is just like kind of, big picture stuff for the exam. It's multiple choice, right? Just know about density stratification, how that possibly led to our formation of the earth, right? And all the layers, to kind of know relatively what order they're in.
How many questions are on the test?
I don't know yet.
Okay.
Currently, we're at 31, but I think the previous years were around 60, so I'm kind of aiming for that. But they should be, like, again, short. I'm just changing it. So plate tectonics, obviously you just want to know Alfred Wegener, that he first proposed it. And so, let's see, just have at least a vague idea of continental drifts. Of course, talking about how they got to it, all the fossils, all the evidence, the rocks. Again, it's multiple choice. So you probably want to be familiar with the Mid-Atlantic Ridge. So what kind of boundary is that? So convergent, divergent, transform. So divergent. So just remember that. What about Himalayan mountains? What would that be? Yeah, convergent. And so that one specifically, right, continental, but I probably won't. Oh, no, I might ask that actually. And San Andreas, which one was that? So transform, good. And yeah, the islands, you just want to know that's from a volcano, but trying to see. Again, it should be just big picture ideas. I'd have to look at a map. Because if it's subduction, though, then it's going to be, yeah, convergent. My only question, is it continental, oceanic then, or what?
It's continent, ocean, Pacific plate.
Oh, yeah, so that would be convergent. And so, yeah, that's oceanic versus your continental. So your oceanic goes under, and that's what drives the volcanoes.
So for the San Juan plate, it's that little mini plate.
Yeah.
Convergent on one side, convergent on the other.
Let's see, so again, just kind of broad things about using satellites, ocean features. So let's look at your notes. I think it's chapter 3. Where's a good picture? So I'm looking for relevant pictures that you would want to look at. So this is probably a nice picture to look at. Hint, hint. You'll probably see a similar picture. So again, I like labeling, so you might expect to see something like this with labels where you have to label the different features. All right, you got your seamounts that are going to be under, your volcanoes. This one just doesn't have volcanoes, but don't forget about your volcanoes. Yep. Yep, so I'm trying to make it easy, but, again, easy, big picture, but we want to do some labeling. And I haven't finished your exam, so I have to figure out what other big picture ideas. I think so far I have 2 open answer, and they're like the math ones, because I want to see people's work and steps, not just blind circling. But yeah, other than that, everything else has been multiple choice. I'm not sure if I'll put any short answers. I kind of like diagram matching more in interpretation. Yeah.
Sorry, is it open though or closed note?
It will be closed note because I am making it broad and hopefully easy. That's my goal. And obviously, right, with any exam, so I always take the statistical analysis of it. And you should definitely take statistics in your time here. I highly recommend. But right, I'm going to look at the average, make sure our average is okay, kind of check out the standard deviation, and make adjustments if I need. I'm always cognizant of that. 'Cause, right, we're here to have fun and learn, not just be penalized. And let's see, what was chat? Oh, wrong class. Yeah. So let's see. I'm just trying to think what I would ask about sediments. Probably something like how far they travel. You know, again, big picture ideas of the calcium carbonate and the silicon. Let's see. I'm actually not quite sure what I'm going to ask yet about this chapter. I have to look at your inspirational notes, but.
So like, when you talk about like how far they travel, like, we're talking about like how the stuff sometimes in that Africa desert extending all the way over here to the East Coast.
Yeah, and I'd probably do like the big picture ideas, like what we were saying, like there are boulders and big sediments are left near the mouth, and then out in the deep sea, that's where you get the clay, yeah. So, you know, it's all, I'll try to just focus on big picture.
Light insect thing, all the way across the ocean.
Yeah, so like sediment classification,
Now,
there's
what
probably,
is this size and source? I was trying to figure that out. What were you actually, what does size and source mean? Like, that's what I was confused about. Because I saw it was like a couple different options. It was like boulders, cobbles, pebbles, granules. And then sources, I assumed, was like the deposits.
yeah, sorry, I'm trying to pull up an exam, the old exam. Because I'm basically basing my multiple choice questions off of like an old exam, but throwing out what I think are the two detailed questions. So yeah, let's see. Yeah, so like maybe something of classifying the sediments. We had the heterogeneous, biogeneous, those sort of classifications. Yeah, let's see. See, I think a lot of these questions are kind of detailed, so I'm going to stay away from them. Might have to get creative with this chapter. But maybe I could make these open-ended of just like where would you see calcium deposits too, or I could make a multiple choice, but that sort of thing. Okay, so I'll try to stick to multiple choices. And then let's see, seawater chemistry. I haven't quite decided what to put there, although we did make it through the chapter, but yeah, I don't know if I should make y'all draw a structure of water. Maybe, yeah, I haven't quite decided, but I will probably put in that chart that we had talked about. Oh, wrong class again, sorry. So remember this chart, I would expect something like that, and you might have to identify like states of matter, like whether that process is evaporation, condensation, something like that could crop up. Steam gas over here, or I don't know what I wrote there now. Oh, boiling. All right, I think we are out of time. But yeah, overall, I don't want people to stress out too much about the exam. But I would probably know like specific heat, no hydrogen bonding. I'll probably have some question about hydrogen bonding. And again, maybe outlining the cycle, the water cycle. Again, just thinking big picture ideas. All right, we will migrate to lab. Your lab's at the front if you want to grab a copy.
But she's, if anything, on the grander scale, trying to make it a little more mellow. So
Yeah.
cross the fingers that way, so.
Yeah,
The intentions and outcomes, with all that goes.
I appreciate that. Well, on my older journal, I meant to write on the front of it with a silver Sharpie, but I couldn't find it. Can you see my name on there good enough, or?
I